Good morning students. Welcome to 11th standard chemistry video class. We are discussing lesson 10 chemical bonding. In our last video class, we completed up to valence shell electron pair repulsion theory. In this video, we will start with the next topic, valence bond theory. Valence bond theory. Hitler and London gave a theoretical treatment to explain the formation of covalent bond in hydrogen molecule on the basis of wave mechanics of electrons. It was further developed by Pauling and Slater. The wave mechanical treatment of valence bond theory is beyond the scope of the textbook. A simple qualitative treatment of valence bond theory for the formation of hydrogen molecule is discussed here. Let us consider two hydrogen atoms, namely hydrogen atom A and hydrogen atom B. It is represented as HA and HB. Hence, these two hydrogen atoms are separated by infinite distance. There should be no interaction between these two hydrogen atoms. Therefore, the potential energy is equal to 0. When these two hydrogen atoms approaches each other, there will be two forces acting, namely attractive forces and repulsive forces. It is explained here. Consider the diagram. Two green color arrow indicates the attractive forces. The first green color arrow indicates the attractive force between nucleus of hydrogen atom A and valence electron of hydrogen atom B. The next green color arrow indicates the attractive force between nucleus of hydrogen atom B and valence electron of hydrogen atom A. Here, the red color arrows indicates the repulsive forces. The two red color arrows in opposite direction indicates the repulsive force between the nucleus of hydrogen atom A and hydrogen atom B. Another two red color arrows in opposite direction indicates the repulsive force between valence electrons of hydrogen atom A and hydrogen atom B. Here, the attractive force tends to bring hydrogen atom A and hydrogen atom B together, where the repulsive forces push the hydrogen atom A and hydrogen atom B apart. Initially, the two hydrogen atoms are far apart. Hence, the potential energy is 0. When two hydrogen atoms comes closer, the potential energy decreases. When two hydrogen atoms comes closer, the attractive force are stronger than the repulsive force. When a stage is reached where the net attractive force are exactly balanced by repulsive force and the potential energy reached to the minimum value, that is minimum energy. At this stage, there is a maximum overlap between the atomic orbitals of hydrogen atom A and hydrogen atom B, and hence they are bonded together by a covalent bond. Now, a covalent bond is formed between hydrogen atom A and hydrogen atom B. Hydrogen-hydrogen bond length is equal to 74 picometer. It is given by internuclear distance. During the formation of the molecule, the energy liberated is 436 kilojoule mole power minus 1. This energy is known as bond energy. Here, the molecule is more stable. If the distance between the two atoms is decreased further, the repulsive forces dominates the attractive forces. and the potential energy of the system sharply increases. Next topic, salient features of valence bond theory. It contains 4 points. Let me discuss one by one. Salient features of valence bond theory. First point, when half-filled orbitals of two atoms overlap, a covalent bond will be formed between them. Consider two atoms. Each atom contains atomic orbital with half-filled configuration. A covalent bond is formed when the half-filled orbitals of two atoms overlap. Second point, the resultant overlapping orbital is occupied by the two electrons with opposite spins. For example, when hydrogen molecule is formed, the two 1s electrons of two hydrogen atoms get paired up and occupy the overlapped orbital. Here, two atomic orbitals with 1 electron each. Now, these two atomic orbitals overlap with each other. Now, new orbital is formed. The new overlapping orbital contains two electrons with opposite spins. Consider the hydrogen molecule formation. Here, the hydrogen molecule is formed by two hydrogen atoms. Hydrogen atom with atomic number 1. It contains 1 electron. It is present in 1s orbital. Hence, these two 1s electrons of two hydrogen atoms get paired up and occupy the overlapped orbital. Third point, the strength of a covalent bond depends upon the extent of overlap of atomic orbitals. Greater the overlap, larger is the energy released and stronger will be the bond formed. Based on the extent of overlap of atomic orbitals, we are having the strength of covalent bond. Greater the overlap, greater will be the energy released and stronger will be the bond formed. Fourth point, each atomic orbital has a specific direction and hence orbital overlap takes place in the direction that maximum overlap. Here, each atomic orbital has a specific direction except s orbital, which is spherical in shape. The orbital overlap takes place in the direction that maximizes overlap. Next, we will explain the covalent bond formation in hydrogen molecule, fluorine molecule, hydrogen fluoride, and oxygen molecule using valence bond theory. Before that, we will discuss the topic orbital overlap. Orbital overlap. When atoms combines together, it forms a molecule. Hence, the atomic orbitals of the atoms overlap with each other to form a covalent bond. Now, a covalent bond is formed between two atoms in a molecule. Hence, we are having two atomic orbitals in which each atomic orbital contains 1 electron. Now, these two atomic orbitals overlap with each other and forms a bond pair electrons. The bond pair of electrons will occupy the overlapped region of the orbitals. Depending upon the nature of overlap, we can classify the covalent bonding between the two atoms as sigma bonds and pi bonds. The symbol for sigma bond and pi bond are shown here. Now, let me discuss sigma bonds and pi bonds. First, let me discuss sigma bonds. When two atomic orbitals overlap linearly along the axis, the resultant bond is called a sigma bond. Again, I repeat, when two atomic orbitals overlap linearly along the axis. The resultant bond is called a sigma bond. This overlap is also called head-on overlap or axial overlap. Here, the overlap involves an s orbital. That is, s orbital overlaps with s orbital and s orbital overlaps with p orbital will always result in sigma bond. Here, the s orbital is spherical. Here, in p orbitals, we are having px, py and pz orbitals. Here, the sigma bond is formed between px orbital and px orbital. When we consider x-axis as molecular axis, the px orbital overlap will result in sigma bond. Next, let me discuss pi bond. When two atomic orbitals overlaps sideways, the resultant covalent bond is called pi bond. Again I repeat, when two atomic orbitals overlaps sideways, the resultant covalent bond is called pi bond. When we consider x-axis as a molecular axis, the overlapping of the py orbital and pz orbital will result in the formation of a pi bond. Finally, sigma bonds are formed due to the linear overlapping of two atomic orbitals along the axis, where pi bonds are formed due to the sideways overlapping of two atomic orbitals. Hence, we completed what are sigma bonds and pi bonds. Next, let me discuss formation of hydrogen molecule, fluorine molecule, hydrogen fluoride and oxygen molecule using valence bond theory. First, we will start with formation of hydrogen molecule. Formation of hydrogen molecule. Two hydrogen atoms combines together to form hydrogen molecule. Hydrogen atom with the atomic number 1. Hence, it contains 1 electron. It is present in 1s orbital. Therefore, the electronic configuration of hydrogen is 1s1. Hence, the 1s orbital of two hydrogen atoms containing one unpaired electron with the opposite spin overlap with each other along the internuclear axis. Hence, overlapping takes place between s orbital and s orbital. Therefore, this type of overlap is called SS overlap. Already, we discussed that axial overlap results in the formation of a sigma covalent bond. Here, a single covalent bond is formed between two hydrogen atoms. That the single covalent bond is sigma bond. Formation of hydrogen molecule is shown here. Next one, formation of fluorine molecule. Two fluorine atoms combines together to form fluorine molecule. Fluorine atom with the atomic number 9. Hence, it contains 9 electrons. The electronic configuration of fluorine is 1s2, 2s2, 2px2, 2py2, 2pz1. Here, the valence shell electronic configuration of fluorine is 2s2, 2px2, 2py2, 2pz1. Here, two fluorine atom contains one electron in their 2pz orbital or one unpaired electron in their 2pz orbital. When the half-filled pz orbitals of two fluorine atoms overlaps along the z-axis, a sigma covalent bond is formed between them. Here, 2pz orbital with one electron of two fluorine atoms overlaps axially and forms a sigma bond. This type of overlapping is said to be pp overlapping. Hence, a single covalent bond is formed between two fluorine atoms. That the single covalent bond is sigma bond. Formation of fluorine molecule is shown here. Next one, formation of hydrogen fluoride. Whenever hydrogen combines with fluorine, it forms hydrogen fluoride. Hydrogen with atomic number 1. Hence, the electronic configuration of hydrogen is 1s1. Fluorine with atomic number 9. Hence, the valential electronic configuration of fluorine is 2s2, 2px2, 2py2, 2pz1. Here, half-filled 1s orbital of hydrogen atom overlaps linearly with half-filled 2pz orbital of fluorine atom to form a sigma covalent bond. This type of overlapping is said to be sp overlapping. Hence, a single covalent bond is formed between hydrogen and fluorine. That the single covalent bond is said to be sigma bond. Formation of hydrogen fluoride is shown here. Next one, formation of oxygen molecule. Whenever two oxygen atoms combines together, it forms oxygen molecule. Oxygen with atomic number 8. Hence, the electronic configuration of oxygen is 1s2, 2s2, 2px2, 2py1, 2pz1. The valential electronic configuration of oxygen is 2s2, 2px2, 2py1, 2pz1. Here, 2p y orbital with one electron or 2p y orbital with half-filled configuration. Similarly, 2p z orbital with one electron or 2p z orbital with half-filled configuration. It is shown here. Here, 2p y orbitals of two oxygen atom overlaps sideways to form pi bond, where 2p z orbital of two oxygen atom overlaps linearly to form sigma bond. It is explained here. When the half-filled pz orbitals of two oxygen overlaps along the z-axis, considering molecular axis as z-axis, a sigma covalent bond is formed between two oxygen atoms. Next, other two half-filled py orbitals of two oxygen atoms overlap laterally or sideways to form a pi covalent bond between the oxygen atoms. Therefore, in oxygen molecule, two oxygen atoms are connected by two covalent bonds. That is, between two oxygen atoms, we are having double bond. In the double bond, one is sigma bond, one is pi bond. The other two pairs of electrons present in the 2s and 2px orbital do not involve in bonding and remains as lone pairs on the respective oxygen. Formation of bonds in oxygen molecule is shown here. Hence, we completed the topic valence bond theory and formation of hydrogen molecule, fluorine molecule, hydrogen fluoride and oxygen molecule using valence bond theory. Let me stop up to this topic. The remaining topics that we will discuss in our next video class. Thank you.